Welcome to EDU World Space.
So for this problem, we are told to consider two concentric insulating spherical shells. So the inner one has radius r1, the outer one has radius r2, and then we're given some values. So r1 is equal to 0.03 meters, r2 is equal to 0.05 meters, and then we know the total charge on each of these spherical shells. So Q1 is equal to plus 6 times 10 to the negative 9 coulombs, and Q2 has total charge minus 9 times 10 to the negative 9 coulombs. And then we're asked to find the voltage at different points in this diagram, assuming that the voltage is equal to 0 at infinity. So just to remind you, the voltage is equal to the integral of dq over 4 pi epsilon naught times r. So for part A, it asks us to find the voltage at r equals 0. So r equals 0 is right here in the center of both of these circles, and so therefore the radius to get to dq will be a constant. It will just be the radius of our spherical shell. So in this voltage integral, we can pull 4 pi epsilon naught r out because those are all constants, and the voltage just becomes the total charge divided by 4 pi epsilon naught times the radius. So remember, this was only because the radius was constant, so we could pull it out. So therefore, the voltage in the center, at the very center, is just going to be this equation added together for both of these two spheres. So this will just be equal to 1 over 4 pi epsilon naught times the total charge on 1 divided by the radius of 1 plus the total charge on 2 divided by the radius of 2. So notice when we plug this in, Q2 is a negative number. So therefore, we're actually subtracting in here. And if you actually evaluate this all, you'll get that the voltage at the center is 180 volts. Okay? So now, for the next part, it asks us to find it at a different place. It asks us to find it at a radius of 4 centimeters from the center. So this radius is a radius of 3 centimeters. The outer one is one of 5, so therefore we're in between the two shells now. Okay? Well, since this point that we're finding at is completely outside the inner shell, remember, since it is spherically symmetric, we can treat this inner shell as if it's a point charge with all the charge right here in the middle of its circle. So therefore, the voltage from the inner sphere is just Q1 over 4 pi epsilon naught times r. And so if all the charge is acting like it's in the middle, then r is just equal to our 4 centimeters. Okay? So we already have the voltage for the inner shell. Now we need to find the voltage for the outer shell and add them up. Now, unfortunately, the voltage for the outer shell is much more complicated because we're at a point inside it that is not a constant radius. So in order to do this, we're actually going to calculate the voltage using the electric field. So the electric field from the inner shell, well, we're outside it, so it acts like a point charge. So this is going to be Q1 over 4 pi epsilon naught r, and then, or r squared, sorry. And for the outer shell, this actually is 0 because we're not enclosing any charge. So the electric field for the outer one is equal to 0. So therefore, in order to calculate the voltage, we're just going to integrate along a path that connects these 2 points. So the center out into this point. And so we could do this because we know the voltage at the middle. The other path that we can take is to come from infinity and come in because we know the voltage at infinity is 0. So this second path is actually the path I'm going to take. So remember that delta V is equal to minus the integral of E dot ds, where S is our path, okay? So therefore, we just get V final minus V initial, and notice V initial is 0. That's why we chose this path, because at infinity, the voltage is decided to be 0, okay? So then this just becomes minus the integral of infinity to R2 of kq over R2, R squared. So this is for this region outside of our spheres, okay? So this is, and I'm sorry, up here I actually had a little bit of an error. So this is outside of the spheres. This is inside of the spheres, okay? So this is out, and this is in. Because if we're outside, they're acting like a point charge. If we're inside, they're acting, if we're inside, then the electric field is 0 because of symmetry, okay? So that's why this is kq over r squared when you're going from infinity to R2. Now we need to do it for the next little region right here, where we're inside. So this is the integral of R2 to R of 0 dr. So obviously this is 0, and we get that the voltage is just equal to the total charge over 4 pi epsilon naught R2, because we plugged in our boundaries here, okay? So then that tells us that the voltage from the R2, or the outer shell, is going to be equal to Q2 over 4 pi epsilon naught times R2, what we just calculated here. And this should be a 2. Sorry that I really messed that one up. But up here, this charge is, we're talking about the outer one, so it's Q2. So now, to get the total voltage at R equals 4, we just add up this one and this one. So we're just adding the voltages, and notice that the charges on the outer shell are negative. So therefore, we're actually subtracting them. So you're going to get Q2 over 4 pi epsilon naught R2 plus Q1 over 4 pi epsilon naught little r, our distance that our point is away. And when you type this all in, you're just going to find that it's negative 270 volts at this center location, r equals 4 centimeters. Now at the next location, they're asking r equals 6 centimeters. So luckily, this is outside of both of these shells, so they can both be treated as if they are point charges at the center, okay? So remember that equation is the Q over 4 pi epsilon naught r, where all the charge is acting like it's right in the center of both of these circles. So the voltage at this point will just be equal to the voltage from both of those point charges. So you have your constants, and then you're going to have charge 1 over r, because we're acting like all the charges in the center, plus Q2 over r, because we're also acting like all the charge from the outside ones in the center. And this just is really adding the charges together. So when you plug these all in, you'll get that the voltage at this point is negative 450 volts per meter. I'm sorry, just volts. Okay, so there's our voltage at our 3 different locations, in the middle, in between the 2 shells, and outside the shell. Okay? Now, what we're going to try to find in part B is what is the voltage difference between the 2 shells. So we have these shells, and we want to know what voltage difference is between these 2 shells. So we're going to pick a path that connects these 2 shells. And we're going to do an integral of the electric field. So remember, delta V is equal to minus the integral of E dot ds, okay? So in order to do this, we're going to have to know what the electric field in between these two shells are. And also, just while we're here, ds is going to be equal to dr, because it's in a radial path that we're integrating. We're integrating straight from the inner shell to the outer shell. So first, we need to do a Gaussian surface so that we can figure out the electric field between these two. So integral of E dot dA is equal to Q enclosed over epsilon naught. Well, my Q enclosed is just the inner charge, and my electric field is a constant. So this will be EA is equal to Q1 over epsilon naught. And so therefore my electric field between these two spheres is just Q1 over 4 pi epsilon naught times the radius squared. Okay? So now we plug this in up here. We get that delta V equal to VR2 minus VR1, because of the direction of the path I chose, will be equal to minus the integral from R1 to R2 of Q1 over 4 pi epsilon naught little r squared integrated along dr. When we integrate this, we're going to get that this is Q1 over 4 pi epsilon naught r, evaluated from R1 to R2, and this will be equal to Q1 over 4 pi epsilon naught times 1 over R2 minus 1 over R1. So now you can just plug all these values in, and what you'll get is that VR2 minus VR1 is equal to minus 720 volts. So the voltage between the two is 720 volts, and since it's a negative number, this tells you that VR1 is greater than VR2.